In example 4, we're going to look at computing limits using the rules that you know for computing limits. So let me just remind you rules. This is theorem 3.1.2 in your book. But the rules are as follows. Let's see, what's a rules color? Orange, maybe? The rules are as follows. If we know that the limit as z goes to z naught of f is m, the limit as z goes to z naught of g is L, then the limit as z goes to z naught of c times f is c times m, the constant multiple rule. The limit as z goes to z naught of f plus or minus g is m plus or minus L. The limit as z goes to z naught of f times g is m times L. And the limit as z goes to z naught of f over g is m over L, provided L is not 0. Of course, if L is 0, you have a problem. All right, great. So let's apply those rules to the extent that we can to compute the following limit. The limit as z goes to I. In fact, actually, we're going to do, let's see, what becomes before A? I don't know. We're going to say 0 comes before A. We're going to just look at the limit as z goes to z naught of something like z cubed. Okay. Now, we've been using the fact that you can just plug in z naught, but we can also write this as the limit as z goes to z naught of z times the limit as z goes to z naught of z squared, provided that both of these exist. So if both exist. Because our theorem doesn't say you can break down the limit like this. It says if the limits exist, then you can break down the limits like this. But they do both exist, so that's fine, as we'll show. And again, provided the right-hand limit exists, we can then further break it down. Like that. And in any world, the limit of the identity mapping, which is what the function f of z is, should be the value you're plugging in. So that's z0 times z0 times z0 is z0 cubed. And in fact, you could use induction. Do you even need induction? Yeah, you can use induction to prove the limit as z goes to z naught of z to the n is z naught to the n for all n in n. So we're going to use that kind of over and over again for these problems. Okay. So I wanted to just go over that real quick. All right, let's do now part A. We're going to look at the limit as z goes to I of the function, which is a rational function. So it's a quotient of polynomials. And the numerator is 3 plus I times z to the fourth minus z squared plus 2z, and the denominator is z plus 1. Okay, so in the first part, we're going to do two of these guys. We're going to really use all of the rules, just to remind you how that works. And then in part B, we're going to not do any of that. We're just going to plug things in to the extent that we can. Okay, so let's see here. Limit z goes to I. Oh, shoot. Sorry, I messed up already. Let me draw a big fraction. Provided the upper limit and the lower limit exist, we can break this up as follows. That is, just take the quotient of the limits, provided they exist. Now we have to show they exist so we can apply the theorem. But provided they exist, this is true. There's no issues with the denominator, right? We can just plug in I, that's fine. With our numerator, we're then going to break them up under plus and minus. In the denominator, we can just plug in our I. There's no issues there. Or actually, let me do one intermediate step just to illustrate something. We'll break this up under plus. Ooh, that's a lot of limit symbols. Now, we can use the constant multiple rule for this guy. So that's going to be 3 plus I times limit z goes to I, z to the fourth. We can actually compute this limit because we went over what happens with powers. That's just plug in I. And then we can use our constant multiple rule here to pull out that 2. So some of these we can just compute. This guy we can compute. And what happens to the function which is always 1 when you plug in numbers closer and closer to I, you get 1. So it's just a reminder. I wanted to do this to remind you that the limit of a constant is just the constant. All right, and now we're in a situation where we can plug in I. My negative I squared is negative 1, and then here we can just plug in I, because now those are just powers. Whew. All right, I to the fourth is a 1. Negative negative is a positive, so we're going to get 3 plus I plus 1 plus 2 plus I. I believe that's 4 plus 3I over 1 plus I. And if we cared about rationalizing, if we cared about writing this in the form A plus BI, we would, and you would find that this is 7/2 minus 1/2 I. So that's a 7. Okay, so that's part A. It's what you learn when you in the first week of calculus, right? Calculus 1, you learn you can do these rules, or maybe the second week, I don't know. For the next guy, we're going to look at the limit as z goes to 1 plus root 3I, z squared minus 2z plus 4 over z minus 1 minus root 3I. And we notice here that we cannot plug in z equals 1 plus root 3I because the denominator is 0, but also you can find that they're both 0. In particular, it's an indeterminate form, and whenever you have an indeterminate form, you then want to see if you can cancel some factor that's showing up. So let me observe here that the numerator factors as z minus 1 plus root 3I and z minus 1 minus root 3I. And the denominator, we can pull out that negative to look to see it's z minus 1 plus root 3I. How did we get this factoring? Well, you use the quadratic equation, and you get that your two roots are 1 plus root 3I and 1 minus root 3I. Okay. And now what do we notice? That term's the same. And now we're in a situation where we can just plug in 1 plus root 3I. So we do that. All right, so we're going to get 1 plus root 3I minus 1 plus root 3I. So I think that's a root 6I. Oh, that's a terrible mistake. That's a 2 root 3I. Sorry. Whew, that's a big blunder. All right, let's mark it. Big blunder happened. What's the blunder? Root 3 plus root 3 is not equal to root 6. In fairness, I'm not done with my coffee. All right, cool. So that's just a reminder of that's just a reminder of the limit rules, and we're gonna see about continuity next.